Welcome to Operations Research. Today, we are diving into the Economic Order Quantity, or EOQ model. Imagine you run a coffee shop. If you buy a year's supply of beans at once, you save on delivery, but need a massive warehouse. If you buy daily, you save space, but delivery fees will bankrupt you. How do you find the perfect balance? That is exactly what EOQ solves. Let us learn how to find this mathematical sweet spot. Now that we understand the basic problem, let us look at the two main forces at play. Total inventory costs are a financial tug of war between ordering costs and holding costs. Ordering costs are the flat fees you pay every time you place an order, like shipping or setup fees. Holding costs are the expenses of storing those items over time, which includes rent, insurance, and even spoilage. If you order in large batches, your ordering costs drop, but your holding costs skyrocket. The economic order quantity is the ideal order size that minimizes the sum of these two costs. Before we build our mathematical model, we must establish the ground rules. To make this calculation work, the basic EOQ model relies on a few strict assumptions that simplify reality. First, it assumes constant demand, meaning customers buy the product at a perfectly steady rate all year long. Second, it assumes instant replenishment, so the moment you order, stock arrives with zero waiting time. Third, no shortages are allowed. You never run out of stock. Finally, it assumes continuous review, meaning you always know your exact inventory level. While real life is messier, these rules provide a powerful baseline. With our assumptions in place, let us build the total cost formula. The total annual cost is made of two parts. The first part is the annual ordering cost. We take the total demand D divided by the order quantity Q to get the number of orders and multiply by the setup cost S. As Q increases, this cost goes down. The second part is the holding cost. On average, you hold half of your order quantity. So we multiply Q over 2 by the holding cost per unit H. As Q increases, this cost goes up. This total cost formula leads us to the most important equation in inventory management, the economic order quantity formula. This formula calculates the exact order size, denoted as Q star, that makes your total cost as small as mathematically possible. It equals the square root of 2 times the annual demand times the ordering cost, all divided by the holding cost. Notice the relationships here. If your demand or ordering cost increases, the math shows you should order more at a time. But if the holding cost increases, storing items becomes too expensive, so you should order less. Before we see where this formula comes from, let us see it in action with a concrete example. A bicycle shop sells 1,000 bicycles per year. It costs $50 to place an order and $10 to store one bicycle for a year. We need to find the optimal order quantity. We start by writing down our given values and the standard EOQ formula. Next, we substitute 1,000 for demand, 50 for ordering cost, and 10 for holding cost. Multiplying the numerator gives us 100,000. We are now ready to simplify and solve. Continuing with our calculation, we divide 100,000 by 10, leaving us with the square root of 10,000. Taking the square root gives us exactly 100 bicycles. This is our optimal order quantity. Now, let us find the financial impact by plugging this 100 back into our total cost formula. Notice that the ordering cost becomes $500 and the holding cost is also exactly $500. They are perfectly equal. Adding them together, the total annual inventory cost is $1,000. The shop minimizes expenses by ordering in batches of 100. Now that we have used this formula and seen that the costs perfectly balance, let us understand where it comes from. We want to find the absolute minimum point of the total cost curve. In calculus, we do this by taking the derivative of the total cost with respect to the order quantity Q. and setting it equal to 0. This derivative represents the slope of the cost curve, and setting it to 0 finds the exact bottom where the slope is flat. When we move the negative term to the other side, we see something amazing. The annual ordering cost exactly equals the annual holding cost. Continuing our derivation, we need to isolate the variable representing the order size, which we now call Q star. We do this by cross-multiplying the terms to get Q squared by itself on the left side of the equation. This algebraic step gives us Q squared equals 2 times the annual demand D times the ordering cost S, all divided by the holding cost H. Finally, we take the square root of both sides to remove the exponent. This leaves us with a single solvable equation. We have successfully derived the famous economic order quantity formula, proving exactly why it perfectly balances the trade-off between ordering and holding costs. So we have proven that this balance holds mathematically. This brings us to a visual representation of what we just did. Look at this graph. The horizontal axis is the order quantity and the vertical axis is the annual cost. The red line shows holding costs rising steadily as you order more. The blue curve shows ordering costs dropping as you place fewer orders. The black U-shaped curve is the total cost. Notice the lowest point on that black curve? If you drop a line straight down, it hits Q star. Crucially, this minimum point happens exactly where the holding cost and ordering cost curves intersect. Now that we know how much to order, we must answer another practical question. How often should we place these orders? We use two simple formulas for this. First is the order frequency, denoted as N. This is simply the total annual demand, D, divided by your optimal order quantity, Q star. It tells you how many batches you need per year. Second is the cycle time, denoted as T. By dividing the total working days in a year, W, by N, we find exactly how many days your inventory will last before hitting 0. This translates a yearly frequency into a daily schedule. Let us apply these new formulas to a factory setting. A factory needs 12,000 microchips a year. Ordering costs $150, holding costs 25 cents per chip, and they operate 300 days a year. First, we must find the optimal order quantity. We plug our values into the EOQ formula. Notice we keep the holding cost as $0.25 to match the ordering cost units. Multiplying the top gives 3,600,000. Dividing by the small decimal makes the number much larger, resulting in 14,400,000 under the root. Continuing the calculation, taking the square root gives an optimal order quantity of approximately 3,795 microchips. Now we find the frequency. We divide the annual demand of 12,000 by our optimal quantity. This tells us the factory will place about 3.16 orders per year. Finally, to find the cycle time, we divide the 300 working days by 3.16. The result is roughly 95 days. The factory should order about 3,800 chips every 95 days, ensuring they never run out while keeping costs at the absolute minimum. We have covered a lot of ground today, so let us review the most important ideas. The economic order quantity model is the absolute backbone of modern inventory control. It solves the fundamental trade-off between the cost of ordering goods and the cost of storing them. Remember, the cheapest way to manage inventory is always found at the exact point where annual ordering costs perfectly match annual holding costs. While real life is messier than the strict assumptions of constant demand and instant delivery, mastering this mathematical foundation is your first step toward understanding complex supply chain logistics. Great work today.